Good morning, friends. Then we are coming to an end almost. We are going to have one more lecture after this, and this lecture is going to be the quite interesting lecture, and it may be right apt to the theme which we have taken, that is a metal 3D printing. And then we have a very good speaker with us now, Dr. Manjaiah. Is assistant professor in our department, that is Department of Mechanical Engineering at NIT Warangal, and is also the coordinator of the FDP, and did his PhD from NIT K Surathkal in 2015, and postdoc from University of Johannesburg, South Africa, and École Centrale d'Inaste, France. And we are fortunate enough, he is going to talk some work where he has done at these two universities on metal 3D printing. If I am correct, maybe wire arc and the DED processes he is going to talk. He has been working in additive manufacturing for the past 5 years, and he has published more than 35 research papers in international journals and conferences, and 4 book chapters. His research interests includes additive manufacturing, surface engineering, statistical optimization, and advanced manufacturing process. Now, let me invite Dr. Manjaiah to deliver his valuable talk. I'm handing over to Dr. Manjaiah.
Thank you, sir. Thank you for the nice introduction about me. Is it my screen is visible?
Yes, yes. So you can go with the full slide mode, sir.
Right.
Yeah, it's visible.
It's fine now, sir.
Yes. And audio is also good. Yeah. Go ahead, sir.
Okay, thank you. Good morning, my dear friends and my dear colleagues. Today in this my presentation, I'm going to make 2 presentations. One is with respect to the powder production and as well as characterization for this additive manufacturing. The another presentation which I am going to talk on the fabrication of these metal parts, especially for the DED process and as well as for the wire arc additive manufacturing process. Okay, with respect to the first presentation, I'm going to talk on this powder production and characterization for this additive manufacturing. Coming to this powder production, why we need to have the powder properties and how it is going to relate with respect to the quality of the parts. Whatever the parts we are going to manufacture with the DED process or with the WAAM process or with the SLM process, powder bed fusion process, means what part quality we are expecting. Means the part properties means one, it may be the density of the part, or it may be the surface roughness of the part, or it may be the mechanical properties of the parts, and it may be the internal build flaws, whatever the defects which are existing in the fabricated parts, and the accuracy of the parts. All this we consider, these are all the quality which we are expecting to have a very good density, very good mechanical properties, and the dimensional tolerance should be very good, and they should be not having any defects in the fabricated parts. These are all the part qualities, properties which we are expecting when we are fabricating with the DED process or the powder bed fusion process. With respect to these expectations, means whatever the part we are fabricating, that is totally depends upon the quality of the powder. Means what quality of powder we are using for this additive manufacturing process, that is going to place a key role in concerning process of this performances and as well as the end part quality. That's why we need to know what quality of powder we are going to use for the additive manufacturing process. The quality of the powder is directly related to the what the production technique which is, how it is produced. That quality is going to give us the part quality of the process. And when you come with these part properties, means in process performance, when the powder is going to be used in the additive manufacturing process, in what process we are using, whether it is a DED technique or the powder bed fusion technique, means in the process how this powder is performing, means in process performance of this powder or the bulk powder behavior, means how the powder is going to behave in the bulk form, and as well as the powder properties. See, whenever we are going to manufacture any component, first we must understand the better understanding, means whatever the required powder properties which we are required for the part quality, means any part we are going to manufacture, we must know the what is the part quality we are expecting, means whether the porous part or whether the very dense part we are expecting, and what type of mechanical properties which we are preferring, means higher elongation properties or only we are preferring for the higher hardness, means depending on the application we must know the part quality which we are going to apply for that. Based on that we can able to select the proper powder that will help us to reduce the cost of the powder production and as well as the facilitating for the choice of the powders. Means there are n number of powder suppliers are there, means when you buy the machines, the machine suppliers will suggest to buy their own powder productions, whatever they are going to give either from the RCAM or either from the DED systems or any other system, they are going to suggest us to buy the same powder from their own manufacturing units. Means first we should know which of the powder and what is the quality we are expecting. Based on that we can get better to go for the other than the offered by the machine suppliers. And as well as according to the Oler review surveys, the Oler is a researcher in this, especially for the powder productions and this additive manufacturing. He has done a lot of research work in this, and he has given some conclusions. Whatever the powder cost is there, that is going to play a major role. That is the second largest cost which is associated with the production of additively manufactured parts. Whatever the parts we are fabricating with this additive manufacturing, the powder cost is the second largest which is associated for the producing the parts. Means that's why we must know what type of powder we are using and how it is going to affect the part quality of the fabricated parts. When we come across with these powder properties, that powder properties can be divided into multiple levels. Means you can see how we are divided into multiple levels. The lowest level of description of this powder properties is the physical properties. The pure physical properties are the chemical properties of an individual powder particles or the powder particles. And the second level of describe this powder behavior is the bulk behavior. How this powder is bulk behavior is existing in the during the process. That is the bulk behavior of the powder. And the third level is description of this powder in the process specification condition during the specific process, either the SLM process or either the DED process, how this powder is behaving in the bulk format with the in process performance. That is the three different levels of the powder behavior in the process. And coming to the powder productions, means there are n number of powder production methods are there. When you go with there are so many productions, the combination of solid metals, the solid state reductions, or the precipitation from the solution treatments, or the thermal decomposition, or the reduction methods, or any electrode deposition or electrolysis methods, or there are automation methods. Means we must choose the which powder production is suitable for this additive manufacturing process. Means when you see that the powder is behavior, how it is going to behave. Means for example, we will take the powder bed fusion techniques. Powder is deposited or spread over the bed is very much influenced by the manufacturing process of the powder, how it is manufactured. Means if you are going for some mechanical methods or some other thermal decomposition or some other methods, it is not going to be deposited evenly over the powder bed. Means it is consisting of so much of finely powdered particles. That finely powdered particles are going to be spread over the layers. That is going to affect when you are going to for the laser sintering or laser melting. That is uniformly it is going to affect the properties of the final components. Means it should be uniformly deposited over the powder bed. And whatever the quality and the size distribution, that is also very much important when you are choosing the powder. And generally for the especially for this additive manufacturing process, we are going to use the major process, the suitable process for this product productions are the gas atomization process, the plasma atomization process, and as well as the plasma rotating electrode process. These are the major three processes which we are using for the additive manufacturing process for the powders productions. Means whatever the powder we are producing, either the single powder production method which is not sufficient for the all the application. For example, the powder metallurgy techniques or metal injection molding techniques or any other mechanical methods. Means the single manufacturing method which is not the sufficient for all the applications. As I told you, the powder production methods can be categorized into mechanical methods, physical methods, and as well as the chemical methods. The mechanical methods is the cheapest method for the powder production, and in the mechanical method it involves the mechanical forces such as the compression or the shear forces or the impact of the forces particles to reduce the bulk material to smaller particles. That is the mechanical method. Example for the milling process, the ball milling process is the mechanical methods of the powder production. And coming to the processes, whatever the process which are suitable for this additive manufacturing the powders, there are many methods which I have told you. The automation is generally viewed as the best way due to geometrical properties. Means this is the best way to use this automation process for the powder production for the additive manufacturing, because we are going to get a very geometrical properties. Means the sphericity of the powder is the very good in this automation process. In that process, we are using a gas automation or water atomization or direct energy reduction. We have to use a appropriate gases for this gas automation technique. Either we can go for the argon gas or nitrogen gas for the automation techniques. And even in water automation, you can follow with the water quenching during the solidification of this molten pool. And we will discuss what about this individuality and how the production is going to take place, this gas automation, water automation in the further slides, and also as well as this oxide reduction under a hydrogen transfer. In coming to this, the metal powder which we are using in additive manufacturing is experiencing a very exponential growth, and with this growth we can have a very new powder suppliers. Means day to day the growth of this additive manufacturing is going to be very increasing. Means we need to have a more number of suppliers of this powder manufacturers. Means the new powder manufacturers and the increased competition in the powder manufacturing methods, the way in which the powder is spread during this additive manufacturing, that is totally depends upon the properties of the powder which we are going to use. And the properties of this metal powder vary widely depending on the automation methods. Means what the properties which we are expecting, like for example we say the flowability should be very good. How we define the flowability of this powder? Means the flowability means the rate of the flow through at a constant orifice. Means in the orifice how the powder is going to flow in the orifice, that is going to define the flowability, as well as the shear strength and the flow energy and the angle of response, and as well as the avalanching behavior, static or the dynamic behavior of the powder. That is going to define the flowability of the powder. That flowability depends upon the flow properties of the powder. The flow properties means it may be the permeability of the powder, cohesive strength of the powder, or it may be the bulk density or the wall friction of the powder, or it may be the compressibility of the powder. That is going to give us the flow properties of the powder. And this powder properties, the flow properties, which is directly dependent upon the interparticle forces. Means there are bulk powder is there. In that bulk powder, there are so many number of particles will be there, a number of particles. That in the particles, how the interparticle forces are existing. That may be the van der Waals forces are there, or it may be the surface tension, or it may be the electrostatic interaction between the powder particles, and how the powder interlocking is done in the bulk powder condition. and how the friction is going to generated between the powder particles. That will give us the interparticle forces that is going to relate to the flow properties of the powder. And overall we are going to tell this the powder properties. Means when we are telling the very good powder properties, which should be the flow properties as well as the interparticle forces and as well as the flowability of this powder. Means how we are going to assess these powder properties. One may be the morphology or the particle size distribution or the moisture content in this powder, and as well as the composition of the powder. Means which will give us the overall the powder properties which we are required for this additive manufacturing process. You can see this the global growth of this additive manufacturing opportunities that is increasing day by day. You can see since from 2019 to 2029, the day to day the powder requirement, the whatever the components which are manufactured by this additive manufacturing process, it is keep on increasing. Means the researchers have shown that the majority of this metal powder cost is going to be increasing highest in the continuous sequence of this additive manufacturing industry. And the quality and the consistency of this additive manufacturing components depends in part and in the characteristics of the whatever the powder which you are feeding into the feedstock. You can see in the right hand side of the graph whatever the value of this additive manufacturing materials as well as the metallic additive manufacturing materials. Generally we are discussing with respect to other the non-metallic materials and as well as this metallic materials. You can see since from 2009 the growth of this trend is keep on increasing till 2013. Again further it is increasing. The study was done only up to 2014. Means you can see this the growth rate, the day by day the powder requirement is increasing because the whatever the additive manufacturing components application day to day we are using, it is increasing. That's why we are requirement of powder is also increasing day to day. And can see this the controlling and understanding of the quality of the powders both in its as supplied as well as reused condition is very much essential. Means we cannot buy powder all the time. Means whatever if you buy the powder, we cannot go for the reused powder. What will happen? The production cost of the part is going to be increased. Means we have to control and understanding the quality of the powder which we are using as the supplied powder and as well as the reused powder is must essential for the this powder production of this additive manufacturing. And this presents a quite challenging to beginners in additive manufacturing technology when deciding the powder suppliers. For example, we need to manufacture some components. To manufacture some components, we are having n number of powder suppliers. Which powder suppliers we have to go for to buy? However, there are so many number of suppliers of the with respect to the additive manufacturing equipment supplier, the machine suppliers, the US suppliers, or the Praxair, or Ognas, or maybe the those are the validated powder in the worldwide. Means the US suppliers or the Praxair or the Ognas, they are the validated powder suppliers in the worldwide. Means the validated powder is identified and which is suitable for this additive manufacturing process. And this validated can de-risk producing the powders for the additive manufacturing. It does not limit the users for a single source suppliers. We are not going to restrict a single source supplier, and also it inhibits the development of in-house expertise. Means we must know that what component we are manufacturing, what is the powder distribution we require, and how this the laser or the electron beam is which is interacting with these powder particles. Means based on that expertise with the in-house system, we can choose the selection of the powder from the suppliers, or you can go for the local manufacturers also. And based on the data from 2013, there are around 855 powder manufacturers are there in the worldwide capable to producing an estimated of 1.12 million metric tons per year to a value of approximately a 6.9 billion of US dollars. Means this is the per year we are using this much of powder for the additive manufacturing process. And there is a potential growth in this additive manufacturing component which is directly related to the increase of the powder suppliers as well as the powder production methods. Means still we are expecting there are so many number of the new manufacturers as well as the new process which we are come across. Means how we have to select the additive manufacturing powder. Means on what basis? As I've discussed the flowability properties, the flow properties, superficial, the particle friction, and as well as the powder production methods. The important method is what is the importance of the powder, means how much it is important the powder is, and as well as what the route of production of that powder is done, and as well as the powder recycling. Means these are the three major importances when you are selecting the additive manufacturing powders. The first one which we are discussing, that importance of the powder, means when we say the importance of the powder during the building sequence of any additive manufacturing component, the raw powder is in the feedstock is stored in an hopper. Means for example, if you go for any DED technique or any SLM technique, the powder is stored in a hopper. That hopper is designed based on the method which you are produced by the machine supplier or the manufacturers of the machines, the build chamber as well as the hopper, that is the own indigenous design from the machine manufacturers. As you can see this, during the building sequence of additive manufacturing component, and the raw materials of the powder feedstock is stored in a hopper. That is, especially in the DED technique, there will be a multiple number of hoppers that can be used for the production of functional grade materials, or it may be the individual materials or the alloy components that can be stored in a hopper and directly entering into a build chamber through the orifice with the help of a pipe, and as well as the stored gas, and as well as the shielding gases with the help of argon and nitrogen gases. And for example, in the SLM technique, a discrete amount of powder from the hopper is spread across the build chamber. Means whatever we have saw in the yesterday's video from our lab, the Manjaiah showed you how this powder is distributed over the bed in the SLM process. Means the powder is distributed in the SLM process on the bed very thin form through by the roller system, or it may be the rake blade system. Means the roller is going to take the powder from the hopper to the bed. It is going to deposit it over a thin layer of the form, in the form of a thin layer, and this no more than 1 or 2 particles of diameters. Means whatever the thin layer is there, not more than the 1 or 2 particles of diameter, and it will be a continuous layer throughout the bed in the SLM process. After this spreading, critically the layer is a homogeneous over the entire area of the build chamber. Any degree of inhomogeneity may resulting in a porosity. Means if there is any inhomogeneity in the spread over the deposit of this powder layer on the whatever the substrate or on the bed, if it is having inhomogeneity, it is going to create the porosity in the fabricated components, or it may be the incomplete through the thickness of melting. During the melting also, it may be the incomplete thickness is going to happen. That is, maybe the too much powder is pulled onto the one particular area. If you are having a one particular area that is accumulated more in that particular area, it is going to create the incomplete. The thickness of the melting will be happening in these things. And the whatever the powder is spread over this the bed, that is either it is interacting with the laser or with the electron beam, depending on the process which we are selecting. Whatever the layer is spreading, hopper dosing and a bulk backing performance of this additive manufacturing powder depends entirely on the properties of the powder being used. Whatever this powder being used, that is totally depends upon the bulk packing factor, the bulk packing ratio, the packing factor of this powder particle normally should be in the 0.5 to 0.7 ratio. The bulk packing factor is the bulk density of the powder with respect to the true density of the powder particles. And whatever we are going to fabricate the actual component, the built volume is significantly less than the total volume of the powder that has been spread over on the build chamber. Means actually the volume of the component is almost normally less than the build volume of the component which is spread on the powders on the bed. As a consequence, there is a large amount of unused powder left over the bed after the fabrication of the component in the build chamber. The given cost of this metal powder is essentially the unused powder is effectively recovered and reused for in a future build. What we can do, there are so much amount. For example, if you want to fabricate in DED process or in the SLM process, there is around 60 to 80% of powder is lost, because how we are designing the component, that is very much important in this SLM process, and how much of the powder is going to be melted in the DED process is important. Means the efficiency of the powder melting is important in this both the process. If you are having a less than 60% of melting efficiency, then the loss of powder will be the more, that again it will be increasing the cost of production of the metal parts which are fabricated with this process. Means we have to use that powder and it has to be atomized or it may be received for the utilization of this in the SLM process or in the DED process. However, the effect of the continued recycling of unused powder on the actual powder properties and subsequent component properties, the component properties has not been the subjective intensively the scientific study, because whatever you are using the recycled powders, that may be consisting of some oxides. I will show you some case studies how if you use the recycled powder, what is going to be happen in the fabricated component when you use for the virgin powder. That we will discuss in the later case studies. You can see the roots of powder production. Means when I am talking about these three major steps of selection of the powders, the importance of the powder and the roots of the powder production. Before going to produce the powder, we must extracting the ore from the ore, and then we are forming by the hydrogenation or dehydrogenation, directly extracting, and then we are going for the post processing of the powder particles, and then we are evaluating whether it is suitable or not. And that is in the first stage itself we can decide, and from the ore we can able to get the ingots. That the ingots can be used for the production of the forming billets or wire billets, or as well as for the gas automation or for the hot water automation. Any type of automation which can use for the ingots, and as well as that ingots can be used to go for this plasma or plasma rotating electrode process or rotating electrode process. This type of automation process also can be used for the powder production. And once we have done this, the automation, we have go for the drying of that powder, that is the post processing things of the powder in the second stage. Then we are have to validate whether the powder is suitable for this additive manufacturing process or not. That is the how these routes of powder production is going to be happen before going to use it for the AM process. You can see there are a number of physical methods are there which we are discussing. Any metal that can be melted and made into a particles to get the powders. Either it may be a pure metal or it may be an alloy powder which we can go for the production, powder production. And the atomization, what do you mean by atomization? Means the breaking of a liquid metal into a fine droplets, typically smaller than the 150 micron. Whatever we are using for this SLM process or the DED process, the powder particle should be less than the 150 micron. Generally for SLM we are using around 0 to 45 microns of the powder particle, that is 5 to 45 micron. And for the DED process we can go up to 45 to 90 or 45 to 120 based on the machine which we are using. Based on that we can choose the suitable powder distribution sizes. And forcing of this molten metal through a small orifice and breaking up into a stream by powerful jets of compressed air, gas, or it may be a water. This is how the atomization is going to taking place to make it into a powder particles. There are different types of automations are there based on the automation media. Whatever we are discussing, the gas and water automation, that is based on the media, and as well as based on the kinds of energy which we are being used for the automation process. That is the centrifugal automation or vacuum automation, or it may be the plasma automation or ultrasonic automation. Coming to the mechanism of automation, how this automation is going to taking place in the powder production. The atomization means it's going to happen in a 4 stages. The first stage is the impingement of an high velocity of jet of water or the gas to produce a sinus wave which causes a distribution in the liquid sheet. Whatever the molten pool is there, in that molten pool we are impinging a very high velocity of the water or the gas to produce a sinus wave to distribute over in the liquid sheet of this molten pool. And in the second stage, that wave fragments and the ligaments formation through a shearing forces because of this high impact velocity of the water or the gas, that produces a disturbance of stages in the one another. You can see in this picture, these are the 3 stages are going to be formed during the impingement of the powder production in the atomization process. You can see in the third stage what will happen, the breakdown of these ligaments, whatever these ligaments are there, these are the ligaments during formation of very high impact velocity of the water or the gas. That ligaments break down into a smaller droplets. That is the primary atomization is going to taking place during the breakdown of that ligament, and the regular particle shapes, that is the high surface tension and as well as the low cooling rates, and there might be a chances of irregular particles also formed in the third stage, that is having a low surface tension and will be having a high cooling rates. And in the fourth stage, the further deformation or it may be thinning of the droplets and wave fragments into a smaller particles can go to occur for the secondary atomization process. The size reduction is limited by the melting viscosity and as well as temperature and the acceleration forces which were acting onto the molten pool. That is in the fourth stage how these powder particles is going to take place. This is the mechanism of the powder production in an atomization process. You can see in this water atomization process in the right hand side picture, we'll be having the feedstock of this alloy process. Whatever the alloy is going to be melted in this furnace and this melting, and then we are impinging a high velocity of water onto that molten pool. Then it is going to form a ligaments, and then as well as it is going to form into the small droplets of the powder particles. And during this process, the melting has a number of variations. But generally, when atomization of water, the feedstock is the first melting furnace before using being transferred into a dish. Before going to transfer into the dish, we have to melt this powder, the production, whatever the billets we are using, that has to be melted and it has to be transferred into the dish. The liquid alloy enters into this atomization chamber from the furnace. From the furnace, what will happen? It is going to through the free fall of this orifice chamber. Through this orifice, it is going to freely fall into this chamber, the atomization chamber. This is the atomization chamber. The water is going to jet symmetrically from both the positions around the stream of this liquid. It is going to making into a small ligaments and as well as the powder particles going to solidify for the formation of the powder particles. This is how the automation process is going to happen. Similarly, gas automation is almost similar to the water automation process, except instead of the water, we are using a gas as an impingement source with a high velocity. In this gas automation process, the mimics of this water automation process means air can be used as an automation media, but it's more likely that inert gas is a suitable process to reduce the risk of oxidation or any contamination of metal in the powder particles productions. Means we have to go for this nitrogen or argon for the gas automation process to reduce the oxidation effects or any contamination of these metal particles in the during the solidification process. And in this process, gas automation process, whatever the powder produces for a high-end applications, means we are using for a high-end application like aerospace application or automobile clothes applications or medical applications. These type of gas atomized powder we are using for a high-end applications. And we need to have a control in interstitial elements as led to increasing the increased use of this vacuum induction melting furnace. Means it is done in a vacuum induction furnace. The stream of this liquid metal is atomized by the high pressure of this jet gases, and due to lower heat capacity of these gases, the metal droplets have an increased solidification time. Means when you compare with this, the water automation process, the whatever the droplets is forming, the solidification is taking place, that is comparatively less in compared with the water automation process, and because of that we will be going to have a spherical powder particles compared to the water automation process. And in the worldwide we are using this gas automation. The annual tonnage of this gas automation powder is much less than the water automation process. That is the 3 lakh ton per year for a air automation and 50,000 ton per year for a inert gas automation for a non-ferrous alloys we are using for this gas automation powder. And the melt size and the melt feed rate, that is less than 120 kg per minute for this gas automation, are lower than the water automation process. And to come across with this mechanism of this melted droplets and the formation of this gas automation process, we have to consider the initial sinus wave. Means how this sinus wave is rapidly increasing with the amplitude. Means that depends upon the flow of molten pool and as well as how much amount of the high velocity impingement of the gas is going to impinging onto the molten pool. and then you are going to have a detachment of wave from the bulk liquid to produce the ligaments, and breaking up of that ligament into a spherical part. That is depends on the volume of the molten pool and the geometric constants, and as well as the injection pressure of that liquid and the pressure of the atomized gas, and as well as the density of the molten pool. Whatever the liquid of that molten pool we are using, the density is also depends. And this diameter is measured with respect to the constant, and as well as this the flow rates of this liquid and as well as the gas. Based on this flow rate, we can able to determine the diameter of the mean particles which we are going to come across in during the formation of this gas atomization process. And during the solidification, either it may be the water automation or it may be the gas automation, how this evolution of the microstructure is going to occur in this the gas automation process or water automation. A minute nuclei or the seed of crystal are formed during the solidification. Means a various parts from the melt pool stream, which is going to grow rapidly and expenses for the surrounding liquid. Means the nuclei is going to form from various parts of this molten stream, and it is going to take place for the solidification. And during the cooling, the nuclei grow more rapidly along the certain crystallographic directions. Whatever the cooling is going to happen during the nuclear formation, that is going to grow rapidly along the certain crystallographic direction, and the resulting into a formation of a branch-like structure. Whatever these branch-like structures are going to form during the solidification and during the crystallographic growth directions, that is called the dendrites is going to form in the solidification process of this powder particle. Even a smaller particles, the small amount of solute elements in the melt pool, that is either in the interstitial alloying element or an impurity greatly affected by the solidification process. Means there might be a chances of impurity, or there might be a chances of some greatly affected the solidification process. These alloying elements or impurities are based on the solidification process, and on freezing, the solute atoms tend to remain in the liquid rather than solidify with the solvent atoms at the crystal liquid interfaces. The solute rejects by the crystal becomes a concentrated in the remaining liquid as a result of freezing. The point of the liquid decreases, and the liquid is just ahead of freezing. The solid liquid interface is more enriched than the liquid is further away, and then the means of the composition of the liquid varies with the distance from the interfaces. The degree of this cooling rate helps in evaluating the relative efficiency of a different cooling techniques for a powder production techniques. Means the magnitude of this cooling rate and its variation in help in interpreting the microstructure of these powder particles. It will help based on this the dendritic growth and as well as the cooling rate and as well as the temperature distribution over these things, and as well as some of the constants. You can see this relationship which was developed between the cooling rates and as well as the dendritic arm growth. That is the lambda is the dendritic arm spacing. With the help of this lambda is equal to k to the power of n. Based on this equation, we can able to determine how the microstructure are going to take place in the solidification of these powder particles. That equation is based, it is applicable for the as well as for the welding process as well as this for the additive manufacturing process. You can see this whatever during the water automation process, these are all the powder particles which are going to come across. There might be a chances of some irregularities. Even though it is spherical, there are some satellites out there, there are some agglomerations out there, there are some non-union the spherical particles are distributed over the things. Means this is going to happen during the water automation process. Means you can see how the solidification taking place. Whatever we are discussed, the solidification, the growth of nuclei and as well as the crystallographic growth direction, okay, a different direction going to form a dendrite. This is how the microstructure of an individual powder particles is going to exist during the solidification of the process. And you can see in the right hand side graph the dendritic arm spacing. Means if you have an increase in the solidification rate, definitely there is a increase in the dendritic arm spacing. Based on that equation, we can able to calculate the increase in this dendritic arm spacing with respect to the different materials and having a different solidification rates. This is from this you can able to different how the microstructure, how the dendrites are going to be formed in the solidification of these powder production methods. You can see the plasma automation is another process in the automation technique, this is the method for producing a highly spherical particles. Whatever we are choosing for the powder production, the gas automation or water automation, this plasma automation helps us to produce a very good spherical particles. In this case, we are using a spool of wire as a powder feed in the feedstock into an automation chamber. Instead of a molten pool, here we are using a wire spool for the powder production, and that wire is fed directly into the automation chamber. With the help of the plasma, we are melting the coaxial torches with the help of the coaxial torches, and with the help of the gas jet, we are going to make a formation of these powder particles. If the powder is provided a long flight path, a spherical shaped powder particles are going to result. This is how we are going to have a spherical particles in the plasma automation process. There are other two automation processes. That is the hydride-dehydration process. This hydride-dehydration process, this method is powder production different from the automation process. It does not involve any melting of the metal feedstocks. It involves the mechanical crushing or milling and screening of the size of the powder particles consisting of some lumps in the feedstock, and then we are going to make it in further secondary process to make a fine powder particles. And nowadays we are having a very recent process, TIRO process. This process is relatively a new method for the powder production, especially for the titanium pure titanium powder, which is developed by the CSIRO Australia. This TIRO process is going to be happening two stages continuous production of powder particles. In the first method, what is going to happen in the first stage, the titanium tetrachloride is firstly thermally reduced to a magnesium chloride and the titanium composite under presence of magnesium in a fluidized bed reactor. We are going to make a composite of the magnesium chloride and titanium in the fluidized bed reactor. Then the magnesium chloride of titanium composite is then separated using a vacuum distillation method to produce a high purity of titanium powder. And in this process, whatever the powder is formed with the help of this titanium powder, which is very much unsuitable for this additive manufacturing process. Why? Because it is having a very large powder particle distribution, that is the 150 to 600 micron. That cannot be used for a additive manufacturing process. Means below 150 only, which is very much suitable for us for the additive manufacturing process. Means there is a necessity of a further modification by the shear milling process or any other ball milling process, which is going to reduce the powder particles of this process. But the thing is, very high purity of the titanium powder can be found with this type of the process, TIRO, the process. And if you see the summary of this table, going to give us the characteristics of the powder based on the manufacturing process. For example, if you see the water automation, we can able to manufacture the powder particles from 0 to 500 micron size. And with respect to the gas automation also, we can able to produce 0 to 500 micron size of the powder particles. And the advantage of this water automation is it is having a high throughput range of powder particle size, only requires a feedstock material in the form of an ingot. In both the process, gas automation as well as water automation, we are using a ingot. And especially this gas automation is very much suitable for the reactive alloys. When you are going to fabricate, when you are going to production of this reactive alloys of that powder, this is gas automation is very much suitable. And also as well as for the oxide materials. And the major disadvantage of this water automation process is post-processing is required to remove this water irregular particles and as well as morphology of some satellites which is presented during the particle distribution. Means which you have shown the micrograph of this water atomized powder particles. It consisting of so many satellites on the over the surface of the powder particles. To remove that satellites, we need to have some post-processing process are required, and also it is going to yield a very low yield that can be 20 to 150 micron. And the satellites is also present in the gas automation process, that is in a less number compared to a water automation process, and which can be water automation commonly used for a non-reactive materials, and this gas automation especially used for the nickel, cobalt, ferrous and titanium as well as for the aluminum powder particles. And the other techniques, the plasma automation, we can able to go 0 to 200 microns. Extremely spherical particles going to happen in this plasma atomization process, especially for the Ta64 titanium powder. We are using this plasma atomization process for this thing. And the major thing is we have to use a feedstock either in the form of a wire or in the form of a powder, which we are already produced with the gas automation or automation process, water automation. That once again we can use it for the plasma automation to produce the extremely spherical particles. And as well as the plasma rotating electrode process, we can able to produce 0 to 100 micron powder, which is having a high purity and highly spherical particles. And centrifugal automation process as well as the hydride and dehydration process, which is the lowest cost for the option, which we are having a lowest cost of production. This dehydrate and dehydration process can be used for the production of water particles. And in this process, it will be having a irregular particle morphology will be there. And coming to the key process variable of these powders and as well as the techniques that can be used during the measurement of these powder particles. Means whenever we are manufacturing the powder particles, we have to characterize that powder particles. Whatever the powders are there, we need to characterize. How we have to characterize the assessment of these things? One is the morphology we can assess. The morphology can be assessed by the optical microscope or it may be scanning electron microscope. What property we can assess? We can assess the apparent density as well as tap density or some of the physical properties of the powder. That we will discuss the what about the apparent density, tap density, how we have to measure that. We will discuss the assessment methods also with there, the air flow meter as well as the cardiac flow meter. Those methods are there. The particle size and the particle size distribution that can be measured by the optical methods as well as by the sieving methods and as well as by the laser diffraction methods. So the commonly used method we have seen in the yesterday's the lab session, the sieving methods. And normally people will use sieving method for the to sort out the distribution range of the powder particles. And the powder particle porosities. How can we measure in some particles consisting of some porosities inside the powders? Means that for that we need to go for the powder particle polishing and as well as with the help of the optical microscope or with the help of SEM, we can able to analyze the porosities existing in an individual powder particles. And also we can able to get the surface area as well as chemical composition of these powder particles. Coming to the morphology of these powder particles, the morphology means the surface area, how it is going to look like, whether it is the spherical or it may be consisting of any satellites or it may be irregular in shape. That the morphology will give us a significant impact. That is going to give us a bulk packing factor and as well as the flow properties of the batch powder production. Means for each batch we have to analyze this powder morphology. Means from batch to batch the powder particle size as well as the properties are going to be changed. For that we need to go for this for all the batches, the characterization process, the powder morphology or the chemical composition or the physical properties are required to the analysis. The spherical or irregular or equiaxial particle are likely to arrange and pack more efficiently than the irregular particles. If the spherical particles are there and having a regularly equiaxial particles, then you will be having the packing arrangement, the packing ratio will be very much efficient when you compare with the irregular particles. And whatever the morphology that can have a significant influence on the powder bed packing density. Means the morphology is very much important in the powder bed packing density of the powder particles and consequently on the final component density, that directly relating to the final density of the component which you are fabricating with the AM process. Where there are more irregular particles consisting in this powder morphology, that definitely going to have a final density of the powder will be very less when you are fabricated with the using of these irregular powder particles. As a consequence of these highly spherical particles tend to be favored for the additive manufacturing process. Means if you have the high spherical particles, that will automatically enhance the flowability properties and as well as the density of the components we are fabricated with this additive manufacturing process. And this limits the use of the potentially cheaper product production routes such as the water automation process as well as the hydride-dehydration process. Means if you analyze the powder morphology, we can able to limit the use of the powder which we are going to use it for the additive manufacturing process. If you know the morphology, we can able to say whether it can be used for the additive manufacturing process or not. You can see here there is a comparison of the different process and how the powder particles, the morphology existing after the powder production. In the first one, you can see the hydride-dehydration process, the gas atomization process, the plasma atomization, and as well as plasma rotating electrode process. This is we have done for the titanium material, especially for the titanium powder. So see the hydride-dehydration process, the powder particles morphology is very irregular. When you come across with this, the gas atomization, the powder particles are very spherical, but there are some small particle distributions also there, and also some satellites are also going to existing in this gas atomization process. Compared to this hydride and dehydride as well as the gas atomization process, this plasma atomization having a very good the spherical powder particles consisting of this. Compared to this all this process, the plasma rotating electrode process having a very good spherical of the morphology of the powder particles, and also as well as the distribution of the powder particles are very good in plasma rotating electrode process. You can see where we are discussing how we need to analyze the powder morphology. Some powder consisting of some porosities, or how we need to analyze the volume of the powder based on very simple methods. For example, if you take the powder particles, we have to put it in an epoxy, and then we have to go for a polishing, and then we can go for a standard metallurgical preparation for the etching and other things. Then we can undergo for the optical microscope or any the SEM analysis to evaluate the whether it is consisting of any porosities and how the surface roughness existing in this individual powder particles, and as well as the volume of these powder particles can be analyzed with this individual powder particle analysis. In some powder particles that cannot be easily analyzed by this SEM process. Means if it is non-conducting powder, some powder particles are there, maybe a composite powders or any other powder particles, for example tin powder particles. In that cases, we need to go for this electroplating of this tin powder particles, or the tin powder particles we are coating a nickel by the electroplating process. Then the powder is the fed into the epoxy, then the polished, and then we can go for the either the secondary electron process or by the backscatter electron process to reveal the microstructure of the powder particles or any the defects existing in the porosities of the powder particles. And you can see this is how we have to analyze after the electroplating of this powder particle, which will give us then the improved surface finish of the powder particles. Means very a sharp surface finish, the smoother surface finish can be obtained by the mechanical polishing. And you can see also with the help of the SEM, if there are any porosities existing in these powder particles, that can be analyzed with the help of this scanning electron microscope. And the major difference between this particle shape and the shape factor, whatever the shape we are analyzing with this optical microscope or with the electron microscope, the major influence is on the processing characteristics, how the process has been done for the powder production, and the usually described by the aspect ratios and as well as the shape factor. The aspect ratio is the ratio of the largest dimension to the smallest dimension of the powder particle existing in that the batch of the productions, and the ratio ranges from the unity of spherical particle to the flake-like structures that can be defined from smaller spherical particle to a flake-like structures. And the shape factor is also called the shape index, and is a measurable of the ratio of the surface area to its volume. The volume is normalized by the spherical particles of an equivalent volume. The shape factor for a flake is higher than its for the spherical particles. Generally, the shape factor will be the difficult for the identify the flake particles. That will be the higher in this case the shape factor, that is the shape index. You can see the other things are there, the characteristics of these powder particles, how we have to characterize the particle size distribution, and there are some other properties, how the size distribution is going to happen in these powder productions. The size distribution is very much important because it is going to affect the process characteristics in the additive manufacturing process. Whatever the flow properties, the compressibility and the density and other properties are directly affecting the metal powder behavior in the processing them. When you are using the process to component, during that it is going to affect the process behaviors. The flow means when the metal powder are being filled into a die. Directly when it is flowing through the orifice, that is going to define the flowability. Compressibility means when the metal powder are being compressed, it is going to define by the compressibility. Density means that is the theoretical density or maybe the apparent density, or it may be the density when the powder is shaken or it may be tapped into the die cavity. That is going to give the density of the powder particles. And these characteristics can be analyzed with the help of this powder particle distribution. Generally for the EBM process, we are using a particle distribution of 45 to 106 micron, and for the SLM process we are using, I told you, 5 to 45 micron as well as 15 to 45 micron process, depending on the which machine we are using. This particle size distribution will have an obvious impact on the both the minimum layer thickness and as well as the resolution of the finest detail in the component. Means which it gives us the finest detail in the component, that depends on the particle distributions. For example, an inappropriate combination of the powder particle size distribution and the layer thickness can be potentially led into an C2 segregation of a due to mechanical recoater polishing porous particles away from the bed. For example, if you take, there are large deviation of powder particle distribution. What will happen when the roller or the blade is going to deposit over the bed? It is going to have a the larger particle is going to be separated from the segregation of this powder bed. In that cases, it is going to have lead to a variation in the build quality. In that case, that space is going to create a void. Means that is going to have the build quality is going to variation in the vertical direction of the component. That is going to create the defects in the components. And using a powder with a wide range of particle size distribution and a very high fine particles consisting to produce a components with a high fractional density. To have a high fractional density, we need to have a wide particle size distribution consisting of a very high fine powder particles. And the use of fine particles, it may increases the risk of the health as well as the safety issue of the operator. And this particularly true when we are working with these SLM machines and as well as the DED process. And some powder particles are reactive materials such as the titanium or some flammable powder particles are there, and also the explosive powder particles. It is going to affect the safety issues. And this particle size, particle distribution, and as well as the shape factor, that is going to define as the powder properties. And as well as this particle size distribution, that is going to define with the help of this normal distribution or with the help of a bar chart distribution. That we are going to have several classes based on the particle sizes. We can classify the powder particle distribution. It may be more than the 50 micron. We are telling it these powder particles are a porous size particles. That can be done with the sieving process. If the fine powder particles are there, then we have to go for the microscopic analyzation or the sedimentation process or any air separation and laser particle size analysis. Means depending on the particle size, we have to analyze the suitable process to analyze the particle size distributions. We can see this the particle size distribution here in the optical images. You can see the image processing can also be used for the analyzing these powder particle distributions. Means how the powder particles are existing in the powders which are fabricated or which are produced with the help of different process. By the identification of color codes, we can able to analyze the powder distribution particle sizes, and also it will give us the normal distribution curve and as well as the histogram curve. See in the right hand side in the histogram, we have analyzed around 4,200 particles. In that, we are going to have an average the particle size distribution is 42 microns. Even though it is consisting of some 0 to 120 micron, the average distribution of this particle size is the 42 micron is consisting of more of these powder particles. And after these things, powder particle analysis, the size factor, all these things, we need to analyze some of the recycled powder. Once we have used the powder for the SLM process or DED process, we need to recycle the powder which we are left out over the bed or it may be left out over in the chamber. To analyze this powder, we have to go for the SEM process. Means initially we analyze the both the virgin powder as well as the recycled powder. When you analyze this recycled powder with the elemental analysis, which we can give us an idea of how much amount of percentage of oxidation is going to occur in this powder particles. The thin layer gives us an how much percentage of oxidation is going to occur in this the powder particles. And from this we have, there are some researchers, and along with our lab we have done so many work with the help of the pure powder, the virgin powder, and as well as the recycled powder. I can see the two scanning electron images of this titanium fabricated with the help of the SLM process. You can see the first images, the SEM images, which gives us an only the alpha structure of a titanium, which we are fabricated with the help of the virgin powder, and there is no number of defects, though there is no large defects consisting in this the virgin powder, purely virgin powder. And when you see this recycled powder in the below, it consisting of a both beta structure as well as in the alpha structure, and consisting of some defects like porosities or some lack of precisions or some cracks are going to occur after the component which you are going to fabricate it. That is mainly because of the recycled powders, and this recycled powders consisting of some the oxide elements that is going to create the defects, or some oxidation is going to affect during the solidification process. That is going to create this type of defects, and as well as it is going to create the beta phases in the deposited fabricated components. You can see some of the examples for this 17.4 pH stainless steel, how we have fabricated with the help of these 3D systems. With the help of some different layers, different hash strategies, we have fabricated this type of some simple components, and then we have analyzed some of the microstructures and as well as the defects. You can see this cross-sectional images of this fabricated components. You can see the growth of this the microstructure along the columnar structure toward the build direction. These are all the solidification layers. For each successive layer, you can get this type of successive the solidification rates, the solidification profiles we are going to have it, and where the solidification interaction taking place between the successive layers, interfusion of the successive layers with respect to depends on the strategy which we are using. Where it is interaction taking place, there you are going to have this type of the unmelted particles, or it may be the porosities going to occur, these type of defects in the fabricated components. And also you can see when you going to use for the some recycled powder, there might be a chance of formation of this oxides in the successive layers. That can be analyzed with the help of this DEM process or with the help of SEM process. Means there is a formation of the successive oxide layers over the deposited layers that can be analyzed with the help of this elemental mapping also. Means these oxides are going to create some of the inclusions in the fabricated components. You can see here, this is a large inclusion which is fabricated in the build components. This is because of use of this the recycled powder when you are going to use for the additive manufacturing process. These are all the defects which you are expected to have in a fabricated additive manufactured parts. And also see here the after this analysis of this fabricated component, we have done some tensile testing, and then we have gone for some analysis of the fracture samples. You can see in that also we will be having some inclusion. These are all the defects which are going to occur because of this oxidations are existing in the recycled powder particles. And coming to the another characteristics, what characteristics we are expecting in this powder particles? The cohesive strength is a important aspect in the powder particles. The cohesive strength means the many metal powders flow like a liquid, and such materials having a no cohesive strength. However, when squeezing into a palm in a one hand, the material is maybe gain enough strength to retain its shape. Once if you open the hand, means that is the it is going to have a sufficient enough strength to enough the retain the shape. That is going to give us the cohesive strength of the powder particles. If the powder gains are under cohesive strength because of the pressure applied into it, it is going to an arc or hat hole can form during the fluidity of this powder. Means it may be created, which if it is retaining its the strength, the cohesive strength, it is going to create this type of the rat or the it may be the rat hole or arc formation in the fluidity of this powder. These pictures depicts the rat hole and as well as this the arc formation in the powder particle that we have analyzed. That is going to show in the next slides. You can see in this thing the next slide. You can see we have done the powder flow analysis with the help of this alflometer based on this ASTM standards B213. You can see here in the first video, sorry, just a second. Okay, you can see here the powder is continuously flowing, means there is no formation of this at all in this, means continuously flow of powder is going to happen, means the flowability is very good. Based on this, the time consumption, you can able to define how the flowability of the powder is consistent. And if the powder is consisting of an cohesive strength, what will happen? If it consisting of a cohesive strength, you can see here in the another video, if it is having a cohesive strength, the powder is not flowing properly. We have to tap or we have to shake the hopper. Means when you are tapping 3-4 times, it is going to form. This is type of the radial formation in the powder particle flowability. You can see I am tapping twice. The powder is not flowing uniformly, and if you see the how this powder is behaving, it is going to create the radial formation in the powder particles. That is consisting of a cohesive strength is more in these powder particles. It will define us if flowability is not good, that cannot be suitable for this for the SLF process or the DED process. Means we have to improve the powder flowability, then only we can use it for the this additive manufacturing process. And some of the factors which are affecting the apparent density. The apparent density means of a metal powder that depends upon the density of a solid material, or the particle size, or the particle size distribution, as well as the particle shape and as well as the surface area and the roughness of an individual powder particles and the particle arrangement. That is going to give us the apparent density of the powder particles. That apparent density decreases with the increasing the particle size distribution, the particle size, and as well as the decreases as the particle shape becomes less spherical or more irregular. If the particles are more irregular, then you are going to have this type of decrease in the apparent density, and as well as decreases with increasing the surface roughness of the powder particles, and is frequently controlled by mixing the various particle size distribution. If you mix with the fine particles and a higher deviation particles, then you are going to have a controlling of this apparent density of the particles. And if you see this table, we are going to have how this particle size and as well as distribution of apparent density. Means, for example, with respect to the different process, the automation process, or electrolysis, or hydration, dehydration process, with respect to the different process, we are going to have a different average particle size diameter. Based on that particle size diameter, you can see the apparent density is varying. If the particle size is 17 of micron, we are going to have a 1.04 of apparent density. If particle size is small, we are going to have a lesser apparent density of the powder particles. This particle density and apparent density is calculated based on the analyzed based on the ASTM B212 standard. And the true density of the powder particles can be analyzed with the help of this Archimedes principle with the help of this gas picometer. And as well as I told you, the flowability can be measured with in terms of the alflometer, especially for the additive manufacturing process. ASTM F3049 is meant for analyzing the flowability properties of the powder, especially for the additive manufacturing. That is standard was the analyzed by the National Institute of Research from USA, and as well as the ASTM F42 standard was analyzed, and they have developed the ASTM F3049 for the analyzing of these powder particles, especially for the additive manufacturing. And these are all the existing methods which we are using for both for powder metallurgy technique or for metal injection molding technique, or this can be used for the additive manufacturing powder analysis. The one is the alflometer based on ASTM 213 standard, and as well as the carniflometer. Especially in the carniflometer, we are using the B964 standard ASTM. And if the powder is not flowing properly, then we have to use the ASTM B417 standard for how much tapping pressure we have to apply, or how much shaking we have to, frequency amplitude we have to give for the analysis of this powder part. When the powder is not flowing freely, then that case we have to use these type of standards. And you can see this tapping density with respect, tapping density always will be higher than the apparent density of the powder particles. If the particles are very spherical, that is 4-point density will be their apparent density, and if you tap it, definitely it will going to increase the density of the powder particle. The tapping density is always higher than the apparent density of the powder particle. That is because of the induction of the lower friction force between the powder particles. That is going to give us an increase in the tapping density of the powder particles. And the bulk packing factor and as well as the flow properties. The bulk packing factor means how the powder flowability is going to occur in the flowability of the additive manufacturing, the powder produced which with respect to the gas or water automation. Means it will gives us the bulk packing factor, means the with respect to the bulk density of the powder and with respect to the true density of the powder, that will gives us a bulk packing factor of the powder particles. Especially for us, spherical particles are generally having a more free flowing than the irregular particles. That is the common thing. The particle size having a significant influence on the flow. Large particles are generally more free flowable than the smaller particles. And if the moisture consisting in the powder particle, that can reduce the flowable properties. Going to create the capillary forces acting between the powder particle, that definitely reducing the flow properties of the powder particles. And the flow properties is often the dependency on the packing density at the time of the measurement. The powder is high packing density, you will be having a less flowing factor. If it is highly dense, means definitely there will be a less flowing properties. In the short range of attractive forces such as van der Waals forces and electrostatic forces can adversely affect the powder flow as well as may cause the particle agglomeration in the powder particles. And we can also analyze this powder particle with the help of this chemical analysis also. By the laser sintering behavior of the metal powder will be not only depend on the physical properties, we can also analyze the chemical composition of the powder particles. That will give us an the depends on the what chemical properties, what course of this chemical analysis need to be done for the analysis. For example, chemical microanalysis can be done with the help of the scanning electron microscope or the electron probe or the X-ray microscopic analysis, that can be done for the chemical microanalysis. And for the bulk chemical analysis can be done with the help of the X-ray diffraction or X-ray fluorescence spectroscopy or inductively coupled plasma atomic emission spectroscopy. With the help of these type of instruments, we can able to analyze the bulk or the chemical analysis. This is how we are going to conclude with the powder production and how we have to characterize the properties of the powder, which is essentially required for this additive manufacturing process. Thank you, my dear participants. If you are having any questions, we can ask. And in between, Srikanth is going to post the quiz session for this session, and we'll have a 10 minutes of break. Then we can go for application of the metal parts with the help of the DED and as well as the WAAM process. Thank you.
Sorry, Manjaiah sir.
Yeah.
ఇప్పుడు పెట్టారా క్వశ్చన్స్ లాస్ట్ లో కదా?
We can put it now also, or we can put last time.
Now itself, okay. Is it related to this topic or
related to only for the powder production? Whatever the quiz I am given, this is only for this.
Okay. If anyone is having asked the questions, we'll continue after 5 minutes.
నారాయణ
చెప్పండి సార్.
ఇది సెకండ్ సెషన్ పూర్తి చేశారు క్విజ్.
2 ఉన్నాయా?
ఫస్ట్ సెషన్ ఇంకోటి ఉంది కదా, అది పోస్ట్ చేయండి.
ఓకే ఓకే సరే సార్. సరే సార్. సార్ శ్రీకాంత్ నాకు అది ఒకటే పంపించాడు సార్. అందుకే అది నేను ఓపెన్ చేసి మరీ చేశాను, కానీ అక్కడ టైటిల్ మటుకు ఇట్స్ లైక్ పౌడర్ క్యారెక్టరైజేషన్ అనే ఉంది సార్. అందుకని అది పేస్ట్ చేస్తాను. కావాలంటే మీరు చూడండి టైటిల్లో, నేను మీకు ఫార్వర్డ్ చేస్తాను సార్. ఐ విల్ కాంటాక్ట్ శ్రీకాంత్ సార్. ఒకటే ఇచ్చారు మీది?
లేదు 2 ఇచ్చిన, లాస్ట్ ఒకటి ఇచ్చి నేను ఫస్ట్ నిమిషం శ్రీకాంత్ కి చెప్తాను, లాస్ట్ పోస్ట్ చేద్దాం.
సరే సార్. మంజయ్ సార్
ఒక్క నిమిషం. నారాయణ
ఒకసారి వాళ్ళకి ఇన్ఫార్మ్ చేయండి సార్. అది I will consider that quiz link when we post that one.
Dear participants, we will post the link at the end of this session also. Both the links will share in the end.
No,
Sorry
don't
for
worry.
the misinterpretation with the scholar. We will post at the end.
మీరు స్టార్ట్ చేసేయండి సార్.
Okay. Dear participants, welcome back to the next session. In this next section, we are going to discuss about the fabrication of the metal parts, which is fabricated by the DED process and as well as the WAAM process. You can see many of the people have already discussed about this. What about the additive manufacturing process? How it is going to be happen with respect to the non-metallic materials, either FDM or the DED or the SLM process. I'm not going to tell much about these things. Just I wanted to highlight from the design to the real part we are going to manufacture. From the design to the real part we are going to manufacture here. Means, for example, if you take any model, we are going to design with the help of a CAD model. That CAD model we are going to generating the slicing and generating the tool path with the help of a CAD model or any slicing software. Then we are using that giving into a manufacturing process, either the DED process or the SLA process. Then we are going to have a manufactured part. That manufactured part consisting of a thermal residual stresses and as well as some of the distortion surface profiles will be there. To eliminate these things, either thermal residual stresses or the distortion surface profiles, we need to go for the post-processing things. You can see here the process constituents are the laser, electron beam, arc, or TIG, or MIG. These are all the heat sources which can use for the fabrication of the components. Either it may be the SLM, or it may be the DED, or it may be the WAAM process. And what are the displacements? The displacements are the robot, gantry, as well as mix of both robot and gantry. And the feedstock, either it may be in the form of wire, or it may be in the form of powder, or it may be in the form of ribbon. And it consists of process parameter. Yesterday, Mr. Lokesh has discussed about how this process parameter are very much important when you are doing for the research thing, especially for the academics and as well as for the research oriented institutes. The process parameters consisting of the laser beam and as well as the beam diameter and scan velocity and the powder feed rate with respect to the DED technique, and as well as the shielding gas, how much rate of the shielding gas we are using, and as well as the powder and the material science, how the powder and the chemical composition is consisting of. That is the process parameter. And the post processing are the art isostatic processing or the heat treatment process or the stress relieving or some of the machining or laser polishing process. These are all the, this is the overall view of this, the additive manufacturing of a metallic powder parts. Coming to see this, why additive manufacturing is such a big deal now? Means everyone is telling additive manufacturing, additive manufacturing. What is the big deal in it? And the big deal means because of the wide availability of the CAD and CAM software. We are having a wide availability of this CAD and the CAM software, and there is a lot of improvement in the automation and as well as the component technologies, and a growing library of these printable materials. Earlier we are having only very specific materials. Now the library of printing materials are keep on increasing because many of the researchers are trying to develop with the new materials. That is the growing library of new materials. The major industry and government investment means the industry partners and as well as the government are investing a lot of funds to develop the new technology additive manufacturing process, and the freedom to operate enabled by the patent expirations. Means we can operate the freedom to operate the enabled patent expirations. The moment, the confidence and as well as creative vision in this technology, and the fast prototyping, we are able to create very fast prototyping, able to fabricate the complex geometries can be able to fabricate, and as well as multiple materials we can able to fabricate the functional grade materials as well as the new materials can be able to fabricate, and it will be having an enhanced performances and will be having a low volume personalized manufacturing. You can able to fabricate even in a low volume components also can be fabricated with the help of this process. Here I am showing a one picture of this, the recently manufactured the IC engine part, the piston cover head. This is the 3D printed part which is fabricated by the Trump laser from the Germany, and which they are collaborated with the Porsche cars. They have implemented this the piston, and they have analyzed how much power it is going to get when you compare with the earlier piston, that is casted pistons. They are getting a 10% lighter of this component when you compare with the forged pistons, and it is going to have a 30 horsepower in this type of piston when you use for the mechanical engines in the car engines. Okay, and also you can see we have heard about the leading edge aviation propulsion, the fuel nozzle in an Airbus or in a Boeing, that is manufactured by the GE suppliers, and it is already implemented and it is widely used in the industry, that is in the Airbus or in the Boeing. Means why we are using these type of additive manufactured component? It is the increases the efficiency of the the engine, that is going to reduce the fuel consumption, and as well as it is going to withstand the high temperature from 800 to more than 1500 temperature. The main goal of this utilization of this, the additive manufactured components, is to reduce some nitrogen oxide reduction, and as well as the service life of the component. The service life of the component can be increased with the help of this additive manufactured components, and as well as it is going to reduce the weight reduction of the component. That will be, and the better fuel consumption will be there in the component. For example, if you take the leaf, whatever I was telling, the GE has fabricated. To go for the traditional manufacturing of that leaf fabrication, in the casting or in the machining process, it is going to have a 20 number of pieces of assemblies are required. Means to fabricate it may take so much of time, and I need to go for the assembly of the process. And in some cases, it is very impossible to machine as a single component, or it is very uneconomical to cast as a single part, that leaf engine part. Means in that cases, we have to go for these type of additive manufacturing process to utilize the fabrication of such very wide application components, either in the medical or automobile or in the aerospace applications. Means this additive manufacturing gives us a freedom. Means this benefits of this additive manufacturing is when we are having a complexity of the components. There is no limit for complexity in this additive manufacturing of components. Means when you compare with this the conventional manufacturing, when the components, the production size is large, then we have to go for the conventional manufacturing process. And if the component is very complex and it cannot be able to fabricate with the conventional manufacturing process, then definitely we have to choose the additive manufacturing process. You can see in the right hand side graph, when the complexity is more, the additive manufacturing process is the best one to fabricate the component, which is widely used for any type of applications. And this additive manufacturing gives us a very freedom to fully design the product without having any worry about the accessibility of the different constituent elements of the parts. Means for any parts we can have a freedom to design, or we can change the shape of the part with the help of the design tools, or with the help of the topology optimization. We can have an efficiency, we can have a freedom to totally design, totally remodify it. And it is one of the fast growing developing techniques in the manufacturing sector. Either you can see in the dental things, or you can see in the aerospace, or in the automobile things. You can see here in this slide the dental crowns and bridges, as well as the implants, which are fabricated with the help of this additive manufacturing process. And the geometry can be scanned with the help of this CAD and CAM software. And we have a majority of the industries already fabricated more than 30 million crowns, and coping bridges has already been made with the additive manufacturing process from the last 6 years. These are all the examples and which we can able to utilize this manufacturing process, the AM process. It is going to replace this conventional manufacturing methods for the customized products. Especially for this medical application, each individual person is different from other, because the bridges or crowns or these implants, the structure of the bone is totally different from one person to another person. In that cases, we need to have a customized products. That customized products can be able to fabricate only with the help of this AM process. You can see these are all the materials which are already undergone the investigation with the help of this AM process. You can see there are a lot of materials are already done analysis, they are already printed, they have gone for the. You can see these are all the microstructures and how the material properties they are compared with the conventional process, from aluminium to the Inconel 708 alloys. These are all the materials which were fabricated. And you can see this additive manufacturing of metals can able to fabricate the functional surface patterns, especially for the healthcare applications, which is fabricated by the Lima Corporate, that is the implant, the knee implant, and as well as the internal structures of it, some conformal cooling channels, what we have discussed by the yesterday our the location, how we can able to fabricate. These are all things which are already fabricated from the SLM process and as well as from the DED process. And also you can have these type of optimized shapes for a aerospace structural application. This is already fabricated by the Ruga, and G is already fabricated the sleep engine. I was telling the sleep injector. This is already applied for the aerospace application. And also we can able to fabricate the lightweight structures, especially for the medical and aerospace application, that can be fabricated with the help of this SLM process. And the major innovative characteristics of this process is we will be having a in terms of shape, the surface properties, as well as internal structure and overall value chain. And this additive manufacturing of metals is similar to like a welding or a sintering process. You can call it as the cladding process, the welding or a sintering process. There are several different metal additive manufacturing processes are there. You can see here the powder feeding technology, that is the laser metal deposition or the direct energy deposition, and the wire arc additive manufacturing and powder bed technology, that is the SLM technology, as well as the electron beam technology. These are all the commonly majoritarily used for the manufacturing of a metallic components with the help of this additive manufacturing process. I'm not going to deep in about the DED process or the SLM process or WAAM process. We already discussed by the earlier speakers, Dr. Kumar, as well as the Lokesh, as well as our Srikant Bantam. Just I'm highlighting how the DED process is going to happen. Means in the DED production, the melt pool is formed on the metallic substrate with a laser beam interaction at the wavelength of the laser beam diameter, which is interacting with the powder particles. In this DED technology, the powder is fed into the molten pool. The powder melts to form a deposit to a fusion bonded to the substrate materials. In these cases, most of the systems are used 4-axis or 5-axis system for the, or it may be used for a robotic arm for the position of the deposition net. And it is having a less freedom to design. Means there is a constraint in these things, because depending on the axis movement, that is the 4-axis or 5-axis, we have to constraints with respect to that axis, and as well as the based on the chamber when you compare with the SLM process. There is some constraints in this DED process, and we need to go for the post deposition as well as the post production heat treatment may be required for this type of components. And there is a post processing final machining is required to achieve a right geometric tolerance, because whatever the fabricated components is there, the surface roughness is very high. To have a better surface finish, need to go for the post processing. You can see here this pictorial view of the DED process. We can use this for the redeposition of the material, as well as for the repair application, as well as we can able to fabricate the direct functional components also can be fabricated with the help of this type of process. And you can see here the production rate when you compare with this DED, SLM process and WAAM process or EBM process. DED will be having a less production rate, and if you compare with the complexity, we'll be having a very precise complexity can be able to fabricate with the SLM technology and as well as EBM technology. If you take the production rate, the highest production rate can be able to obtain with the WAAM process, because wire is using as a feeding material, that we can able to fabricate it 9 kg per hour, the production rate of this in the WAAM process. You can see this beam video, how this powder is interacting with the laser. You can see here the laser is coming from the center. In this case, they are using a coaxial nozzle. The powder is fed coaxially through the nozzle, and as well as along with a shielding gas. We are going to have, this is how the deposition is going to taking place in the DED technology, and it is having some constraint because of this the axis movements and as well as the chamber, the size of the chamber. You can see for the repairing purpose or as well as for the functional part building purpose, we can use this type of the DED technology. Okay, see some of these things which is very close to welding. This whatever the additive manufacturing we are talking, the DED process or SLM process, which is or SLM, it is very close to the welding technology. Means either the powder or either the wire is directly interacting with the energy source, and it is going to melt and it is going to deposit. It's very similar to the welding technology. You can see the production rates of a different process. For example, if you go for an electron beam or a laser beam, in the case of that, you can able to fabricate the wall build up to 7 to 8 millimeter per hour. That is the production rate with respect to the SLM process. When you go for the beam process, we can able to fabricate it 2 to 3 micron. Means the multiple dimensions or the beam dimensions vary in the electron beam 2 to 3 micron, and for the laser 0.5 to 1.5 microns of the melt pool. And with respect to the deposition rate, you can see you can able to have a deposition rate of 5 gram per minute. When we are going to have this the DED process, we can able to fabricate even less than 25 gram or 5 gram per minute, or we can go up to the 35 gram per minute also in the case of DED process. And with respect to the selective laser melting process, this is the process which we have seen already in the yesterday's lab session. This is accepted in terms of the ASTM F42 standard, and this is also known as direct metal laser sinter, and which is most frequently used for the aerospace medical application fabrication of these components. I'm not going to explain how the process is going to happen. And in this process, whatever the components we are fabricating, the layer between the fabricated parts, that is the layer is between 0.02 millimeter to 0.1 millimeter. That much very thin layer able to fabricate with this SLM technology. It cannot be able to fabricate this much thin layer with the help of this the DED technology, because the beam diameter itself is very large. We can have a beam diameter of 0.5 millimeter or 0.2 millimeter or 1.2, or we can 2 millimeter also will be there in the case of DED technology. But in the case of SLM process, the laser beam diameter will be around 45 to 75 micron. Can able to fabricate very smaller bead diameters. And the average powder particle size which we are using for this SLM is a 35 micron. That is what I have told you. That is between 15 to 5 to 45 micron. That can be used for the SLM process. You can see this is how the SLM process is going to work. You can see these are the examples which are possible to fabricate with this SLM techniques. Means this is the strut structures and the rocket engine. This one is which was fabricated from the courtesy of this SLM process. Already fabricated this the rocket engine, and these are the some dental medical implants, and which is already fabricated within our lab for standardizing testing the machine 3D systems. Means I am showing here how much complexity of the components can be fabricated with this type of techniques. And the major highlights of this SLM process, whatever we are discussed with this the rocket engine also can be fabricated with this SLM process. Means with the help of this inconel material, they are already fabricated the SLM manufacturers. In this, it is going to have a minimal post processing required. When you fabricate this SLM process, minimal post processing is required in spite of whatever the complexity is there, and to avoid the tooling wear as well as the difficulty in the machining of this nickel based wire, that can be fabricated with this SLM process. And this innovation is the direct integration of multiple parts and internal features. Example, the internal ducts that can be avoided with this type of process. And improved function, cooling due to innovation lattice structure, which also increases the stability of the component. And the efficiency, the minimization of individual process steps by combining multiple of individual parts. Means if you combine n number of parts or assemble n number of parts, it is going to reduce the efficiency of the components. Means that can be efficiency improved by this type of fabricated with the SLM components. And you can able to fabricate very lightweight structures, which is very much essential for the lattice structures for the biomedical applications or weight reduction for the aerospace application. That can be fabricated with the SLM process. You can see the market situation and competitiveness of this sector. day by day it is increasing in all the sector, or the commercial sector, medical sector, automotive sector. The day by day, the utilization of this, the application of this, the additive manufactured metallic components are day by day it is increasing. And the major industrial barrier with these additive manufactured components are there. One is the geometrical defects. That is very difficult to control the geometrical defects. Means we need to have an online monitoring system to control the geometrical defects, and as well as the residual stresses and the porosity and the impurities or contamination existing in the fabricated components. And also the production rates. If you want to go for a higher production rate, definitely these type of the defects is going to existing in the component. And there is a limited stability and repeatability of the process going to have a major barrier for this industrial breakthrough of this additive manufacturing systems. These are the expensive materials are already fabricated, the titanium materials or the other materials. And today there is no commercial system is available for automatically detect the defects during the process. Means there are n number of manufacturer suppliers are there, SLM or the concept laser or beam technology or 3D systems, whatever we are saying, they are the developers of this machine. But there is no the commercial system to have, because once we are manufacturing component with 3D system, we cannot compare with the other type of the SLM process. That is the major drawback of this the additive manufacturing of metallic components is there. That is the repeatability or the comparison between the process to process is very much challenging issue in this type of this metallic components. And also the online monitoring system, automatically it has to detect the defects when it is fabrication going to occur. That is the challenging issues in this the additive manufacturing system. Here I will show you some process map with respect to the SLM process, especially for fabrication of titanium 64. You can see here in the graph there are different zones are there, from zone 1 to zone 3 and as well as the OH. That OH is the serious surface deformation is occurring in the fabricated components. In the zone 1 means with respect to this laser power and scan speed are very much important to optimize when you are going to fabricate the components. Means the scan speed and laser power is very much essential. If you either increase or decrease, definitely you are going to have a defects in your components. You can see in the zone 1. Zone 1 is the optimized laser power and then optimized scan speed. In that case, you will be having a very good fully dense components can be able to fabricate it. In the zone 2, you can see here the subsurface porosity due to excess heating. This is the zone 2. In this zone 2, what we are doing? We are increasing the laser power and we are keeping at a lower scan speed. In that cases, what is going to happen? Because of the excess heating, it is going to create these type of the defects in the fabricated components. And if you keep a lower laser power and you go for a higher melting speed, that is the scan speed, it is going to happen the insufficient melting. Because of insufficient melting, there is no proper diffusion takes place between the successive layers. In that case, it is going to have this type of the lack of defects or the bulk porosities are going to happen in the fabricated component. This is the major process map between this laser power and the scan speed when you are fabricating any type of metallic components. And there are so many issues with respect to this, the DED process or the SLM process. There are several issues are there. We will discuss some of the issues here. The material processing issues. For example, when you are fabricating some components, you can see this surface topography of the fabricated components will be having some typical layer thickness will be there. That layer thickness depends on the process, either it may be SLM or EBM or it may be DED process. That thickness you can see here 10 micron, it may be 50 micron or 250 micron. You can see these are all the whatever the surface profiles between the vertical successive layers is there. That is going to define as the geometrical scaling and as well as the surface range which were expected. You can see here there is a non-flattened layer of edges will be there. The whatever the layer is there, it is totally a rough surface. The actual surface roughness of this metal is going to happen in this part. This is the surface which you are going to have with respect to each individual layers. You can see here, for example, a successive layer. The single layer if you take, in that single layer there are multiple number of the unmelted powder particles will be there. That unmelted powder particles, when you deposit a second layer, it is going to create the defects for the second layers. Means this irregularities is keep on adding in the successive layers. This irregularities definitely creating the some defects in the fabricated components. This means the longer build time because of the layer thickness dictates the division of the part into a number of layers. That is going to give us an idea of these material issues or the how it is going to happen. The another issue is the build chamber atmosphere issue. It is strongly affected the chemistry of the component and as well as the processability and the heat transfer. The build chamber is very much important. The inert gas and or a vacuum system are typically used for each requirement, leads to unique processing concerns. Most of the metal powder tendency to oxidize and collect moisture when it is exposed to air, because when you are using this metal powder, almost normally aluminium or you can take titanium materials, it is normally tendency to oxidize with respect to the air. And in the DED process, inert gas is used as a shielding gas flow over the meltable surface to protect the oxidation. And especially in the SLM process, typically it is operated in an inert gas atmosphere environment. And especially for the EBM process, we are using a heated filament to generate the electrons, which is requires a vacuum capable of a build chamber to operate the machine. That is, the less than 5 into 10 to the power of -2 Pascal chamber pressure is required, and as well as this column pressure of 5 to 10 to the power of -4 Pascal is required when we are going for the EBM process. Means the build chamber is very much specific with respect to the process, either EBM or either SLM or the DED process. And there are another issue is the feedstock quality. When you are fabricating component, you want to have an important quality of the final part. Means what type of feedstock you are using, whether it is wire feedstock or it may be a powder stream feedstock or it may be a radial symmetric powder nozzle or it may be a coaxial nozzle. Means based on these type of powder feedstock quality, we are going to have a quality of the component can be analyzed. Means the surface morphology or the shape or the internal porosities or some defects, that is going to can be occurred by these type of feedstock quality of the things. And also as well as the quality of powder determines the physical variables such as flowability and as well as the apparent density, what we are discussing the powder properties as well as the powder characteristics. That is very much important when you are using these type of different feeding systems. And you can see I have told you powder is very much important. The quality of the powder which we are going to use for the SLM process or for the DED process are very much important, because the shape of the powder, if it is irregular powder, satellites are consisting, in that process there might be a chances of some internal porosities are existing. That powder quality is very much important. That depends on the what type of production technique which we are using for the production of this gas atomization or rotary gas atomization or plasma rotating electrode or plasma automation process. And for the WAAM process, definitely there will be a minimal defects when you compare with the powder process, because the technology for wire making is already transferred from the matured welding consumable supply chains, because it is already developed. Definitely there will be a chance of the defects will be less in the WAAM process when you go for the production of the wire or for the powder. And there are some challenges in this metallic additive manufacturing process. Means the additive manufacturing process requires a high quality of powder. Whatever the powder we are using, it should be very high quality. There should be no contamination, clearly no moisture existing in that powder, and size of the powder particles and as well as the shape of the powder particles. Means this is the very much important and very much challenging to produce when you are go for the production of this powder. And no mix of powder charges are consisting, and reuse of remaining powder is also a challenging issue, how to reuse it. And the another challenging issue is the beam powder interaction, how this the electron beam or laser beam which is interacting with the powder. The interaction of this heat source with the feedstock or the melt pool impacts the utilization of energy and can lead to a liquid metal ejection and as well as the porosity in the component. There are 4 basic modes of particle ejection during the the laser beam interaction with the melting process, that is convective transport of a liquid or vaporized metal out of the molten pool, the melt pool. The spattering ejection is going to taking place during the interaction of the beam and as well as the powder. And the another one is the electrostatic repulsion of the powder particles and the kinetic recoil of the powder in the DED technology, and enhanced convection of a powder in a gas stream. These are the major basic modes during going to happen in the powder interaction with the laser or the electron beam. You can see here whatever I was telling you, the spattering or the powder interaction. You can see this is going to be happen, the scattering or extraction of the powder particle when you are going for a DED process. And some powder particles partially melted will be, and what happens if you partially powder melted particles are deposited on the surface, and what particles are melted in the melted pool, means in the molten pool it is whether it is in the state of in the air it is melted or in the flight mode or it is melted in the on the substrate, and it's the combustion of both the two powder particles, and what is the percentage of input particles going to the fabrication, means the efficiency of the powder particles melting, that is very much important. There are some particles multiple reflection, especially for aluminum, lot of reflection will be there in the aluminum powder particles with respect to the laser. And these are all the important challenges when you are going for a complex metal fabrication, metal part fabrication. And the another challenge is porosity. This is the major drawback in metal manufacturing, that is the porosity. This is the common defect which you are going to occur in SLM process or in a DED process. That porosity may be the powder induced. If powder is consisting already some porosity, definitely it is going to induce into the part. Or the process induced during the fabrication, the process may also induce because the lack of the argon gas, or it may be the because of the lack of vision between the layers. That may be depends upon the hatching strategies or the process control variables, that is going to induce this process induced defects, porosities, or the artifact of solidification. Even some cases, if you are having a chromium content or sulfur content in the material, that sulfur is going to have creation of this artifact solidification, means it is going to during the solidification it is going to create some cracks or the defects in the component. The process parameters must be properly tuned, properly optimized to avoid these type of the defects going to occur in the components. With the optimized melting process parameters, process induced porosity can be reduced to a very less level with the help of DED process or SLM or the EBM process. Less than 1% we can able to control with the fine tuning of the process parameters. And the another thing, major issue is the scan strategy. To build any component, what type of strategy we are using, means we cannot go for the simple strategy or common strategy for fabricating all the components. Depending on the shape of the component, geometry of the components, we have to choose a proper scan strategies. Either it may be unidirectional, bidirectional, or it may be the spot melting, or it may be the chessboard, or it may be the line melting, or it may be the zigzag or snake filling. There are a number of strategies are there. We will discuss some of the strategies, how it is going to affect during the fabrication. And for the outline and as well as for the inside filling also, we have to choose a different strategy when we are fabricating the component. And also for the wall fabrication and for the some cylindrical objects or different complex surfaces, we have to choose a different strategy for fabrication with respect to the different process parameters range also. And the another major drawback, the challenging issue is the cracking and delamination. The formation of these type of defects are essentially depends on the temperature of melting, temperature of solidification. This cracking of this microstructure may occur due to the solidification and as well as the subsequent heating. The heating is taking place subsequently in this ready manufacturing process, that is going to create this type of the cracking defects. And these macroscopic cracks may relate to the other defects, including the porosities. The solidification cracks can occur from some materials if too much of energy is applied. If you are using more than the required amount of energy, this type of solidification cracking is going to occur in the fabricated component, and that may induce some stresses in the fabricated components between the solidified areas of a melt pool and as well as the areas of a yet to solidify the layers. That is going to create this type of stresses. Ultimately, it is going to have this type of defects. And there are other defects of the delamination defects between the successive layers. And the another one is the melt ball formation. If you are not optimizing the scan speed, definitely you are going to have this type of the balling effect in the materials. If you are having a higher scan speed, you are going to have this type of the multiple balls are going to form in the deposited layers. You can see with respect to different variation of the scan speed, this is how we can able to optimize the ball formation reduction in the with optimizing the scan speed. And you can see here, if you are having a highest scan speed, you'll be having a this type of the balling effects, melt balling effects will be there, and there will be a humping effects will be there. If you want to have a stable track, we need to optimize the power with respect to the scan speed. That is very much important in this metallurgy manufacturing to have a very good weld bead structures. And the another thing is the residual stresses. This is the common the defects, the common drawback in the metallurgy manufacturing component. That is because of the thermal gradient during the processing, and it can negatively impact the mechanical properties. If the residual stresses are more, definitely it is going to affect the mechanical properties and the driving forces challenging to a grain structure of the components. If the stresses exceeds the local yield stresses of the material, it is going to create the wrapping or the plastic deformation of the metal may going to occur in the components. If these stresses exceeds the local ultimate tensile strength of the material, it is going to create the cracking or some other defects are going to occur in the components. The macroscopic residual stresses can have a dramatic effect on the bulk behavior of the additive manufactured parts. If the macroscopic residual stresses are there, definitely there will be a bulk deformation or bulk changes will be there in the component compared to the atomic dislocation or the microscopic residual stresses. You can see here, this is with respect to the macroscopic deformation. That is because of the macroscopic residual stresses, the bulk deformation is going to take place in the fabricated component. This is the how we are residual stresses is there means this type of defects is going to occur in the fabricated component. And this is with respect to the comparison between DED and SLM. This is already discussed by the Srikanth Gunta in the last session. No need to explain more. I will discuss some of the case studies which I have done during my research work from the past 5 years with respect to the DED process. This is how the laser beam interacting with the powder and the thermal hysteresis, and as well as the surface structure, whatever the structures we are going to have that geometrical properties, microstructure, residual stresses, and we need to have some post-process additive manufacturing operations to enhance the property or the geometry of the component. You can see one examples I will give here. The air duct we have fabricated, this air vent in the small size, small scale, as well as in the big size also we have fabricated. To fabricate this air duct, the laser diameter which we are used is 0.5 millimeter of laser diameter we used, and this is how the shielding gas and as well as the powder flowing is going to occur in this DED technology interacting with the powder. To fabricate this component, we not only choose a single scan speed or a optimized laser power, because the shape of the component is deviating from the starting to the end. Means we need to have the strategy is linear strategy we are used, linear zigzag strategy. To have this strategy with respect to that, we have continuously varied the scan speed, because whatever the scan speed are there, that is the optimized for fabrication of this type of structure. If structure is changing, we need to optimize the scan speed with respect to that power is used. Initially we are using a higher laser power, and then later we are using a lower laser power with a high scan speed rate to have a better microstructural properties as well as mechanical properties. You can see here, these are all the process parameters which we are used, the gas pressure as well as the powder flow rate, and we are going to have in this build direction how the surface roughness will be there. You can see here, there are sticking of unmelted powder particles will be there in the fabricated components, and there are some balling effects in the end layers, in the last final layers will be there, because we are melting at very high speed with a low laser power. In that cases, we are going to have these type of the drawbacks, the defects are going to occur in the fabricated components. And the another major issue is the ripple or wavy surface effects on the part integrity with stitch layers. When you are stitching the multiple layers, successive layer decoration, we must know what is the contact angle of this weld bead, how this weld bead is going to occur, and as well in the successive layer, how the contact angle is changing with respect to the each individual layer deposition. You can see in this photograph, in this image, you can see for the multiple layers, for we assume that theoretically whatever the substrate is there, it is a fully the flat surface we are assuming. And this theoretically deposition for the successive layers also we are assuming the whatever the layer deposition is the normal the curved surface of layer, and it is going to have a flat surface we are assuming. But in some cases when we are depositing successive layers, there might be a chances of this type of the lower defect surface or irregular surface will be there. With respect to this irregular surface, we are assuming this is the normal standoff distance between the nozzle and the substrate layer. In some chances, we are going to have increasing the standoff distance. Because of this increasing the standoff distance, definitely there will be a molten pool changes variation is going to occur because of the interaction of the photoparticles and the laser beam. And in some cases, it is going to have a lower standoff distance between the nozzle and as well as the substrate. That is going to definitely change the contact angle of each individual layer. That is going to have these type of the successive stitch layers, wettability is going to change, and this wall thickness is going to change, and we are going to have a different type of the expected geometries can be occur. Because of this, the minute defects also is major important in this surface, that way we affect the surface roughness of each layer, and this type of defects are angle of wetting angle is very much important when you have to go for the metallurgical manufacturing process. And with respect to the cross-sectional layers of the fabricated component, you can see a formation of this rippled wall is going to happen when you are going for a successive layers. You can see in this microstructure, there are the melt fusions is going to occur in the fabricated components. We are going to have these type of the equiaxed dendritic structure. We are going to have this type of the columnar structures will going to occur in the fabricated component with respect to the DED stainless steel materials. And you can see the major facts and challenges in this additive manufacturing of metallic components is the major issue is the heat transfer, the fluid and continuum mechanics, and as well as the melting, solidification, solid state transformation between the layer to layer, and the grain growth and diffusion of the textures. That is very much important when you are going for a remelting of layer. You can see in this left hand and right hand side, I have shown you the convex profiles and as well as concave profiles. That is the solidification profiles when we are using for the deposition. Means definitely this is very much important, because the successive solidification layers, if you are having these type of layers, these type of inverted layers, the mechanical property will be the poor in this case. And if you are having these type of concave surfaces, definitely you will be having a higher mechanical property. That we will discuss in the later. This balling effect is also going to occur when we are having a highest amount of scan speed. That is going to occur in the highest scan speed of 1200 millimeter with a less laser power. This is because of the some Monaghan effect in the melt pool or in the weld bead. It is going to happen this type of things. Why it is going to happen this type of things means the positively skewed surfaces may be particle size distribution containing a very high fraction of smaller particles. If the powder particles containing more than fine particles, smaller particles are more, that type of the balling effect is going to occur, and it may be negatively skewed, means it is having consisting of a larger particle. And this formation of this balling defect is the initiates from the void formation of the center of the molten pool between the molten pools, and this void is going to expand. It's going to create the melt pool or the balling effects in the weld beads. If you are having a faster travel speed and a lower laser power, this is going to increase the likeliness of forming the balling effect. And you can see this how the microstructure is going to originate in this the additive manufactured component, which is very similar to the welding. I tell you, it's very similar to the welding technology. And you can see this from starting takes place, the solidification takes place from the outer side of the wall to the center of the component. This is how the dendritic cellular components, the cellular structures we are going to have. That very much depend upon the thermal gradient and as well as the rate of solidification rate. Depends on these things, the thermal gradient and the solidification rate, the cooling rate. We are going to have this type of the cellular dendritic structure in the fabricated components. And also we can able to control the grain growth structure from the deposition rates. That is how much quantity of powder is melting and how much laser power using and what is the laser beam diameter and the scan speed. From these things, we can able to control the grain gauge structure in the fabrication of the components. You can see in the right hand side, we can able to optimize the deposition rates with respect to the formation of equiaxial grain structures that can be controlled with the controlling the process parameters. And we have evaluated the microstructure of as well as the microharness properties of the fabricated component. Throughout the components, if you optimize properly the process parameter, we can able to fabricate very good components, very good, highly uniformly distributed tensile as well as the microharness properties. We are, you can see, almost all we are having a 262 to 220 HV of hardness we are getting into when we optimize the process parameter. And also we have done some surface topology studies. Means when you fabricate the component, definitely the surface is very rough. We cannot able to use that type of component for the application. And as well as in the internal curved surface, will be having this type of structures will be there. To eliminate or to have a better surface finish, we have gone for the laser polishing. That is the post processing done. We have done to remove the surface roughness to enhance the surface properties. You can see here after surface laser polishing, we will be having a this much of surface roughness we are going to have in the laser polished components. The post processing techniques are very much important to eliminate the rough surfaces. Depending on the need, we have to choose either it may be the mechanical or chemical or it may be the laser polishing. And for the definitely for the high load parts, arc isostatic processing is very much important. It is mandatory to have the heaping process for the arc isostatic process for the high load parts and for the having a better mechanical properties. You can see we have done EBST analysis also. You can see the grain structure is the columnar grain structure. It is keep on growing towards the build direction, and the grain size is also very high. And to control and if you go for this post processing treatment, we can able to have this type of a lower grain size structure and as well as a like reduction of the columnar length of the grain sizes can be done with the help of this the post processing treatments. And we have done some the mechanical properties for with respect to we have compared with the fabricated component as well as the wrought alloy components. You can see here this is how the comparison made. The mechanical properties are almost similar when you compare with the tensile properties. Only the reduction is the elongation property. That reduction of elongation is because of the defects is going to occur in the component. That is maybe unmelted powder particles or some porosities or it may be the lack of fusion. That is going to create the reduction in the elongation properties. These are all the defects are going to occur in the fabricated component that definitely going to affect the elongation property, but the mechanical property tensile strength will be very good in this type of fabricated components. And also we have done some repairing and as well as functionality parts with respect to different inconel material 625 as well as monel material. We have deposited multiple materials to evaluate the properties, and with respect to the inconel and this monel material, in the transition zone they will be having a lower hardness properties because of the heat affected zone compared to the base material. And when you go for this type of different 17.4 PH steel or 13 chromium steel, the interface in the between these successive materials, two materials, substrate stainless steel material or the inconel material with the stainless steel material, in the interface zone will be having a highest amount of hardness because the material property is suddenly changing and also it's going to formation of heat affected zone and also the microstructural effect is going to have a highest hardness in the interface zones. And we have done some energy efficiency optimization process to fabricate some simple walls. Means when you fabricate with a walls with a different scanning speed as well as different laser power, what type of the solidification profiles we are going to get it. And if you do not optimize, we are going to have, for example, generally we are using 1 kilowatt laser power, then you are going to have this type of the solidification profile, the concave solidification profiles we are going to get it. That definitely it is going to have a less mechanical properties. The mechanical properties is poor in this type of because the solidification profiles which will use us in the bonding strength between the successive layers. And how we have to monitor this means we need to have some feedback systems to coincide the geometrical dimensions and as well as this profile that can be monitored by the temperature, width and as well as height knowing to that bead is not regular or inherent to challenging the interfacial angles on the rough or contaminated surfaces underneath the successive layers. That can be controlled only when we are having, means that can be the surface waviness or contact angle or the deposition width or accumulation of heat. If you have this feedback system to analyze these type of things, then we can able to go for the online monitoring with a very good successive components. And you can see these are all the convex and concave melt profiles are going to happen when we are having a different laser powers. That definitely is going to affect the mechanical properties of the components. And we have done a simple analysis for fabricating some cylindrical components. This is going to be late, sorry, I want to quickly finish up these things. We have done different strategies to build the cylindrical components. You can see we have considered 4 different strategies. Which one is the best optimum strategies to fabricate geometrical as well as good mechanical components, mechanical properties as well as microstructural properties? In these 4 strategies, we have done so much of strategies. This is the linear strategy for fabricating the cylindrical component we have done. Similarly, the outer layer, we can choose the different strategy. For any single internal filling also we can choose a different strategy. Means if you are choosing the different strategy, all the 4 strategies, circular, linear, zigzag, will be having these type of difference. If you go for the circular continuous strategy, there is no stop and stop interaction between the laser and as well as the powder, then you are going to have a very less defects, very minute microporosities will be there, and also geometry also will be very good in the fabrication. Okay, this is the example we are optimizing the starting process strategies to fabricate the cylindrical components. And also we have done some analysis for the titanium materials also to evaluate the mechanical properties. This is how we have planned for the testing. We have used a titanium 64 material from the Proxair, and we have fabricated, these are all the different components. This is the as fabricated component, and this is the layer spacing, the delta Z, as well as the strategy which we are using 45-degree inclination zigzag strategy we use to fabricate the component. This is the heat treated samples. The surface is definitely going to be oxidized because we have not done in a vacuumized atmosphere, because we have done in a heat furnace, heat in general commercially heat treatment furnace. The surface is oxidized, and we have done some surface roughness analysis. Definitely the fabricated components will be having a higher surface roughness, that is of 20 micron we have got in the surface roughness. This is how the surface profile will be there in the fabricated components. And these are the successive layers we are going to have the diffusion of the successive layers when in the fabricated components. And we are also going to reveal the how the microstructure is going to happen. The columnar microstructure keep on going towards the building direction in the fabricated components. And this is what is going to happen. This is the alpha as well as the beta, because the TA64 consisting of alpha plus beta alloy, and these are the structures we are going to have in the fabricated components in the beta grain boundaries and as well as the alpha colony structure, which can be very much comparable to the normal wrought alloys in the common techniques, conventional manufacturing. We have also done the difference between the mechanical properties, the microhardness properties of the fabricated and conventional manufacturing. It is almost similarly we have variation of around 50 HP of hardness. We have got variations, and also the mechanical properties in all the directions. Even is the repaired components also we have done either both the direction or in the single direction repaired components. You can see here the tensile difference between the fabricated components with the different extraction of samples from the rectangular blocks. The mechanical properties is almost same as the wrought alloys. Only thing is the elongation properties is very poor when you are going for the 45-degree inclination or when you are going for the repair components, because this is definitely because of the Young's modulus is almost same in all the components comparable with the wrought alloy materials. This elongation is reduction is mainly because of the defects. You can see here the porosities are in the intergranular structure, or it may be a this type of defects like a lack of fusion between the material successive layers, or it may be there some unmelted powder particles are there. This is going to definitely affect the elongation properties. That can only be improved by the heat treatment process or some further post processing process that can be improved elongation. We have also done the low cycle fatigue and as well as edge knot tensile testing to evaluate the mechanical properties. The fatigue properties are almost matching with the rot alloys, and as well as the crack propagation is almost matching with the crack propagation testing with respect to the rot alloys, with respect to all the extraction of the samples from the fabricated. The summary of this analysis of this DED technique is, we have to finely tune the energy to eliminate the crack-free functionalized surfaces, especially for the repair application, and also with a little or no dilution from the base metals. And also embedded powder particles and the last deposited particles are because of the highest scanning speeds. And the particle-free lower deposition indicates the complete melting, and some oxide traces are going to exist. The absence of texture and ferrite, crack-free, low, less than 5 microns of porosity, fine grains with the cellular microstructure can be obtained with the optimization of process parameter. Rough surface with a poor cosmetics are visibly layered structures with a lower speed. Means when you are having a lower speed, definitely you will be having a rough surface are going to occur in the fabricated component. We need to have a go for the post processing, either laser remelting or go for the machining techniques. And some of the future challenges and future directions of this additive manufacturing, either DED or WAAM process, the online monitoring via in situ sensors, that is very much important, and the integration and synchronization of image acquisition with respect to the machine controllers, and the big data stream management for a continuous process monitoring, and also the study of multiple multi-sensor data fusion methods to enhance the process monitoring performances, and as well as the coaxial, off-axial sensing, the processing, the monitoring multiple levels, and as well as the evaluation of novel in situ sensing solution is required for this, the DED process or as well as SLM process. This is some of the components which are fabricated with our lab. Some of the application components we have impeller and as well as the gas turbine blades, implants, which is fabricated directly with the DED process. You can see some of the turbine, air duct I have told, and some of the components, and the very thin wall also we have fabricated. These are the components which are fabricated in the DED process. And even with the other WAAM process, just I will go to show you what is the major drawback in WAAM process. The major drawback, these are all the components which are fabricated in the WAAM process. The major drawback we are in the WAAM process is the porosity is the major drawback. These are all the components which are fabricated in the WAAM process, and after for the successfully application for the aerospace application, when you are going for a structural application, especially this WAAM is very much useful for the structural application. You can see the very simple example I will show you. You want to build a core structure with the help of different axes, either 3 axis or 5 axis. In the 3 axis we can able to build it, but the defects whatever we are getting, the deformations defect is the more in 3 axis machine when you compare with the 5 axis machine in the WAAM process. And the another major drawback is the porosity which you are going to have in this, the aluminum fabrication with the help of this WAAM process is very much large. To eliminate these porosities means we have to go for the heat treatment process or go for the rolling process. With the help of some other Cranfield University along with Central Land, they have developed a rolling process to go for the deposition. After that, continuous rolling of simple structures. This cannot be used for some complex structure. It can be used for only for the simple structures. Like this, they have developed a continuous rolling over a successive deposited layers. This will enhance the mechanical properties, and it is going to have a, because of the rolling, it's going to have this type of equiax structure. Definitely, this equiax structure will be having the highest mechanical properties compared to the unrolled components. And these are all the functional grade materials, bronze and steel we are fabricated in our lab with the help of the WAAM process. And this is the spider graph which is defined by the Cranfield University, and the benefits of this WAAM process compared with this DED technology or the SLM process. When we are having a structural component and we need to go for the cost saving and as well as the flexibility of the platform, we have to go for this WAAM process. And if you want to having a highest build rate, also we can go for this WAAM process. And if you want to having a very complexity, we have to choose a powder bed fusion technology. And based on the requirement, we have to go for this type of the process. This will give us what process we have to select based on the part size or flexibility or the cost saving methods. Thank you, everyone. This is some of the simulation we have done for the WAAM process. If you have any questions, please ask. Thank you for very much and patience for listening this much elongated talk. Thank you very much, friends. Participants, if you have any questions, please ask. Otherwise, you can close the session. Narayana, is there any questions?
No, sir. No questions, sir. If anyone is having, please ask this.
Hello.
Yeah.
Hello.
Yeah.
Sir, I wanted to know that um, is there any research scope in the like field of residual stresses, like managing residual stresses of metal 3D printed parts?
Definitely, it's a challenging issue. Control the residual stress in the fabrication of these metallic components because the
Correct.
continuous melting and remelting is going to take place in this the metallic additive manufacturing process. Because we need to monitor the temperature distribution and as well as the cooling rate. Then only you can able to control the residual stresses. That online monitoring is a challenging issue for the this additive manufacturing process.
Okay. So, sir, like
Go for this analysis.
conform can conformal cooling channels help in this matter?
Conformal cooling channel it will help, but only for depending on the application. For example, how you are going to control the solidification rate of the material when you are going for DED or SLM process. We cannot
Yes,
able
yes.
to create a chamber to cool down, or we cannot able to create some heating coil in the below the substrate. We have done so many analysis that is working for the WAAM process. With respect to this
Correct.
DED and SLM is a very challenging issue. How to control the solidification? That's the major issue
Yes.
with DED and SLM.
So, sir, is there any like theoretical kind of a thing which can be applied?
Theoretical.
Theoretically, like, is there any theoretical solution for that which
Theoretical
can be
solution
applied? Like,
thing is
no, no.
we have to monitor the temperature and control the grain structure. That is
Sorry,
a major thing is required.
sorry, I didn't hear.
The temperature control means we must know the solidification rate of the material, and when
Yes.
you compare with the welding process, there are so many standards and online monitoring systems are developed with the welding process. Those things we need to apply for this additive manufacturing of metallic components also.
Okay, sir. So can I, like, if you don't mind, can I contact you later for this? Like,
Yeah, you can send me by email. You can contact.
yes, yes, sir. Okay. Please provide your email.
Thank you.
It's the website.
NIT Warangal website में तो ఉంది sir.
It is
Yes,
there
sir.
manjaiah.m at nitw.ac.
Okay, okay, okay. అక్కడ నుంచి తీసుకుంటా.
Sorry?